That's kind of the issue. So now it's for lectures for campus.
Wait a second.
Do you post the recorded lectures?
Yeah.
Okay.
Yeah.
I had a brain fart yesterday, just thinking that class started at 5. Also, something fell off. I looked at my schedule like crap. I was no point coming in.
Yeah. So the best place to find it is like on from the homepage.
Uh-huh.
I post it every week, and so it's organized by that. And so like this is for Finite elements, but on every weekly page there's a section called recorded lectures, and this will take you straight to YouTube for that.
Okay.
Yeah. So the ones for both the ones for biomechanics are up this one. Yeah.
Okay, cool.
Yeah.
Dr. Chan, how's your day?
What's up?
I said, how's your day?
That's good. A little sleepy today. I had a hard time going to sleep last night, but that's doing good. How about you?
Not too shabby. Did good on our problem definition or a problem project proposal for senior design. So
Okay.
riding that way.
So how does that work? Do you guys write a proposal and then your senior design professor approves it or gives you feedback on it?
Yeah. So they give us, he gives us a guideline for our professor's Dr. Mayoral. So he gives us a guideline to follow and kind of briefs us on what is expected of us to write, and all that contains in it, including a budget, a breakdown structure of how the rocket's going to work and all the parts and sub teams and what we're looking for. We give them a full budget breakdown, even a schedule timeline of our estimated like time to design, time to build, and so forth. And then we give it to him for evaluation, and he can say, "You're horrible, rewrite the whole thing," or he gives us like feedback that says, "Yeah, this is good. Change this, this, and this," and then next week submit it to the department. Kind of gives us a proofread.
Okay.
Which is nice.
Okay. Yeah, that sounds like a good process.
Pretty well.
You guys have a pretty cool senior design setup here, though. Like when I was in college, my senior design project was everyone had to do the same thing. And so there's no room for like, proposing or no room for, doing your own thing. And so everyone was kind of, working on the same kind of robot, basically. It was fun in its own way. They kind of made a competition out of it. And so they had all the teams compete to see who could design the robot that would complete the task the best. But it would have been cool to see if we could work with like industry or, kind of do our own thing.
So what was your design then?
They had this big ramp, and we basically had to design a robot to carry these huge like cinder blocks up the ramp, drop them off into a bin, and then come back down the ramp. So the competition was whichever robot could drop off the most cinder blocks in like 10 minutes or something like that, then they win.
Yeah.
One of my biggest regrets from college was when we made our robot from our senior design team, we took the first letters of all of our last names, and then we made that the name of our robot. And so we made a robot called Coastbot because that was we just had all the letters for that. But we didn't realize that we could have used the same letters to spell tacos, and so we could have been Coastbot instead. And I think our professor marked us down like 1% because of that missed opportunity.
The taco bot.
Could have called yourself Taco Bot and
Yeah.
gotten everybody's laugh. Yeah. We called our rocket Daedalus
Oh, really?
Okay.
after the Greek inventor and architect.
Cool.
I prefer the layman version. Daddy lust.
Daedalus. Did we need to? We don't need to fire up SolidWorks at all for this, did we? Because I noticed that a couple of the files were SolidWorks files. Am I right?
They're SolidWorks files, but they're formatted already to work with ANSYS, and so you just need ANSYS.
All right. I didn't know if we had to you were going to make us practice on saving them as file types or not.
Oh no, I'm pretty sure you guys can do that. So I'm not going to make you do that.
Yeah, this activity is interesting because before dedicating my full-time status as a student, I used to work at a sign company, and I was in charge of designing the CAD blueprints on how to assemble it. And these center poles were very popular to design, and it's really interesting seeing the other side now because the company usually had engineers do the analysis for them to determine what structural pole is best fitted for these types of signs against the wind.
Nice. Yeah, you're going to be doing exactly the other side of that. So now you're going to be the engineer doing the analysis now.
Yeah, that's really cool.
Dr. Tran, it's my birthday on Saturday, so if you could have the Taco Bot drop off some tacos for dinner, I would appreciate it.
You can ask one of your friends to Postmate it for you. That'll be
Won't be the same as a Taco Bot, though.
I've heard they've been doing some testing in certain neighborhoods of an actual autonomous robot to deliver stuff for, I don't know if it's Postmates or Grubhub or what, but I know they're doing some testing for it in a while.
Is it the one that's on? Is it like the one that's on wheels that rolls
Yes.
around?
Yeah.
Yeah, I've seen that one.
Yeah, I think they were testing in San Jose or something like that. Well, happy early birthday. Hope you have a good birthday.
Yeah, it's going to be met with a little bit of dinner with family and a lot of studying and homework. You know, the way birthdays should be celebrated, I guess.
It's the college way.
Yeah, makes me still feel young.
Sorry, Professor, did you say we don't need the SolidWorks file, right? Yes.
Oh, you need the file, but you don't need to open SolidWorks itself.
I see.
Yeah, yeah. All right, guys, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. All right. All right, so today is an ANSYS day, and so we're going to be doing an activity today. And so, I'm going to be talking a little bit at the beginning of class, and so for everyone in the class, if you can open up ANSYS Workbench right now and download the instructions and the CAD file from Canvas, then we'll be ready to get started. Okay. And so if you go to the assignments page on Canvas, you can click on ANSYS Activity 3 for the signpost. And then I want you guys to download the list of instructions here, right? And so that's the PDF file, which has all the instructions. And then I want you to download the first CAD file here, right? And so it's going to be the solid signpost geometry. There's another CAD file there, but just like the first activity, this is going to be for kind of like an extra credit problem at the end. And so you're not going to need it, probably not going to need it today, but at the very least, you're going to need this first CAD file and also the instructions. Okay. All right, and so I'll give everyone a chance to download that and open up Workbench. And in the meantime, let me talk a little, or just mention briefly that I posted up the midterm project. And so I don't know if Canvas sent you a notification for this, but I did post up your information for the midterm project. Okay. And so you can download the specifications and the CAD files for that here. Okay. I don't want to talk about it too much right now because I want to make sure we have enough time for the activity. But on Tuesday, I plan on spending probably the first 10-15 minutes talking about it just to brief it for you guys. Okay. But if you want to take a look and get a sneak peek, you can download it. And it's going to be due on October 29th. And so I'm giving you guys a little bit over a month to do it because it's because honestly, this is the first time I'm running this project. And so I'm not sure, you guys are kind of like the guinea pigs in a sense. And so, I want to make sure you guys, I give you adequate time to work on it and work through all the kinks and to work through the writing and stuff like that. Okay. Because not only do you have to do the finite elements for this one, of course, but there's going to be a significant writing portion as well, because you have to turn in pretty much like a finite element project report. Okay, but we'll talk about that a lot more on Tuesday. Okay. All right. Okay, and so back to the activity for today. And so you can see that the subject for the activity is a signpost. Okay. And in fact, if you look at the dimensions for the signpost, you can see that it's about 28 feet tall. The dimensions for this match about what you would expect from like a freeway signpost. Okay. And so these are the signs that you see over the freeway, which tell you, where your exit's going to be, how many miles until, Nutwood Avenue, things like that. Okay. And so we're going to be running a finite element simulation on this and using those finite element results to actually design the post a little bit better. Okay. And so, quite a few new things in the assignment for today. Okay. All right. Can't think of anything else. I think that's it for my announcements. And so, before we really get into it, are there any questions I can answer? Okay. All right, so let's go ahead and get into it, right? Okay, and so first thing to do, so let's open up ANSYS Workbench, and then we're gonna add a static structural simulation, just like we always have, okay? And so in static structural, we have all of these things, right? And so the first thing we're gonna do is we're gonna add a custom material property, and so we're gonna follow the same process that we followed in activity 2. And so let's go ahead and double click on engineering data here. And then we're going to add the exact same aluminum, 6061 material here. So I'm going to type in aluminum 6061. Okay. Right. And then just like last time, we're going to add isotropic elasticity. And so with aluminum 6061 highlighted, let's go ahead and double click isotropic elasticity. Okay. And that's going to allow us to specify the Young's modulus and Poisson's ratio. Okay. Oops. Why does it always do that? All right. And so if you look into the project specifications, you'll see that the Young's modulus for aluminum is 1 E7 psi. And so this is really important because a few people yesterday were getting weird simulation results because they didn't pick the right units. Okay. And so you want to make sure that the units for your Young's modulus is psi. Okay. So make sure you do that. And then let's go ahead and set the magnitude here for 1 E7. Okay. And then the Poisson's ratio is going to be 0.33.
Go back, you went really, really fast right there.
Oh, say again?
Did you go back? You went really, really fast.
I think the internet was kind of weird. Okay. Yeah, so for this one, we're basically just creating a new custom material. And so if you go back to your workbench home, you go ahead and double click engineering data right here. Okay. That's going to open up your material data sheet for this ANSYS activity. Let me do this from scratch again, just so you can see. Okay. All right, and so in this box right here, we're going to click to add new material, and we'll call it aluminum 6061. Okay. And then just like we did with activity 2, we're going to add isotropic elasticity. Okay, so let's go ahead and double click that. And then we need to specify here the Young's modulus and the Poisson's ratio. And so make sure that your units for the Young's modulus is in PSI. And so let's go ahead and set this to 1E7. And then the Poisson's ratio is going to be 0.33. Okay. All right. We're going to do one more thing here because we actually need an additional property for this activity because we're actually going to apply the weight of our aluminum sign. And so in order to compute the weight, we need to know the density of our aluminum as well, right? And so with aluminum 6061 highlighted here, we're going to go ahead and double click on density. Okay. And so if you did that right, you'll see a new entry down here for density. Right, and then we're going to input the density for aluminum. And so let's see. And so the units for density here are going to be pounds per inches cubed. And so make sure you pick the right units for the density right here. Okay. And the density we're going to put in is 0.0975. Okay. All right. So is everyone able to add in the Young's modulus to Poisson's ratio and the density for our aluminum material?
I have a question.
Sure.
So when we just input all the parameters that we need and then we just like come out, then it just deactivates the option to change it.
Mm-hmm.
How can we just like, kind of like make it active again in order we want to like, change the density or whatever?
You mean after you run the simulation, like you want to change?
No, I just like input the numbers,
Yeah.
but when I click on the engineering data and my aluminum 606126,
Yeah.
is the isotropic elasticity option
Yeah.
just deactivated? It's kind of like gray.
Oh, so once you've added it to your aluminum, then you can't add it again. So you're basically saying that this is grayed out right here.
Exactly.
And so it's already added to this material. And so because it's already added, they do this to show you that you've already added those
In
material
order I
properties.
want to change it, I need to delete it and then recreate.
Oh, if
it.
you want to change it, you can just change the value in this box right here. And so let's say if we want to change it to 1E6, and so that changes it right there. And so these things on the right here, these are, you can kind of think of these as like containers for these material properties. And then their values are actually set down here. But you can.
It's just not opening this down here. That's the thing. So I just click on the isotropic elasticity, but because it's deactivated, it's not opening this chart.
So this menu down here is missing. Down here.
Yeah, exactly.
Okay, so you need to reset the view, and so you click on view right here, and you're going to click on reset workspace.
Got it. Thanks.
Yeah. Mm-hmm. Yeah. So whenever you guys, because I know ANSYS has a lot of these like extra windows right here. And so if you ever accidentally close one or if you kind of lose one, you can always click on view and then reset the workspace or reset the window layout. And then that will bring the menus back. Yeah, what's up?
Could you repeat the density again?
Yeah. So the density is 0.0975
Okay.
pounds per inch cubed.
All right. Thank you.
Yep. Okay. Any other questions on the material properties here? Okay. All right, and so let's go ahead and close that, and let's go ahead and import our geometry, right? And so hopefully you guys have downloaded the solid signpost geometry base. Okay, so let's go ahead and right-click on geometry. We're going to import. And apparently I didn't log off yesterday, and so it actually still saved it. So, but go to where you downloaded the solid signpost and just add that in. Okay. And this part here was actually made within Design Modeler in ANSYS, and so there shouldn't be any compatibility issues or anything like that. Okay. All right, and so with that done, you can go ahead and double click the model here, and then that's going to bring up ANSYS Mechanical. And so if you loaded the geometry, it should look like this, right? So we have our signpost here. And we have like a little nice kind of rounded face. Yep.
Right here in the handout, you say structural steel is the default material analysis, and we will take the default structural parameter.
Yep.
What do you mean by that?
So the structural steel is a material that's already loaded within ANSYS, right? And so when we created aluminum here, there was already one here called structural steel, and things like its Young's modulus and the density and things were already. They've already been set, and so we don't need to create a new one for that. That's all I mean for that.
Oh, okay.
Yeah. Mhm. All right. Okay, and so within ANSYS mechanical here, we can see our geometry, right? And so today's going to be the first time we work with an assembly of parts, right? It's not the most complex assembly, but it is technically an assembly, right? And so we have 3 parts to our geometry. And so if you go to the geometry section here from our project outline, okay, and then you click on the plus arrow next to geometry, you can see the 3 parts that we have, right? And so if you click on the parts, you'll see them highlight in the 3D window here. And so let's start with the sign. Okay. And so when you click on the sign, you can see that the gigantic rectangular sign here is highlighted. We'll click on the post, and so the post here is highlighted there. Right. And then we also have this this question mark surface, right? And so we have this this body called WX2 application surface, right? And what you'll notice for this is that there's kind of a blue question mark right here, right? Whenever you see that blue question mark in ANSYS, what that's telling you is that ANSYS wants you to specify something there before you can continue, right? And so basically what it's saying is that the specification for this surface or this setting or whatever it is incomplete, okay? And you'll see another example of the blue question mark here next to static structural, okay? Right. And then for that, and then for the one down here, what that's saying is that we haven't specified any boundary conditions yet, but you know, we're still working our way towards that, but you know, but we'll get there. But you know, this blue question mark is you know, ANSYS kind of always uses it for the same thing. And it's to indicate to the user that you need to specify something else. Yes, yeah. So the geometry was imported, and so if you download the CAD file from the website, and you can import that just like we did with activity 2. Yeah. Okay. All right. And so what is this application surface here? And so to see what this surface is, we have to kind of rotate the signpost around, okay? And you'll see that we have this little beam of you know, it almost looks like a piece of tape that runs from the top of the signpost to the bottom, right? And so what this surface does is that question?
I accidentally imported the wrong one.
Uh-huh.
How do I change it?
The best thing would be to just to start a new project. And so go ahead and close ANSYS Mechanical, and then you're going to click on this button right here for a new project.
Okay.
Yeah. All right. And so this, what this surface is going to allow us to do is that this surface is going to allow us to apply a boundary condition on this side of the signpost, right? Because if you go back to the specifications for the activity, you'll see that on the left side of the signpost we have this this spatially varying force right here, right? WX2, and that's acting on the entire left side of the signpost, right? And so in order to actually supply this force on that location, we need to basically give it a place where we can click onto it, right? And so without that extra surface there, it's actually going to be really hard, because if you try to click on any other surface around here, right? And so let's say that we try to click on on this horizontal surface on the side of the sign, you can see that it highlights this entire surface green right here, but it doesn't highlight anything on the post, right? And so we would only be able to apply a boundary condition on this side, right? And then similarly, if you try to click anywhere on the cylindrical post, what you'll see is that it'll turn the entire post green, right? And so this isn't really what we want either, because we want to make sure that the force is only applied on this left side right here, okay? And so what and it wasn't me, but the person who made this geometry did, was they basically took a strip and then they sketched it in Design Modeler and then projected that sketch onto the geometry right here, okay? And so this is what I call like a phantom surface in ANSYS, right? And so it's a surface that doesn't actually exist. And so it doesn't add any kind of volume or any kind of structure to the to your geometry, but it's there just for the purpose of letting you apply a boundary condition, okay? And so it's really just like a phantom surface or a ghost surface. And so we don't really want it to be there, okay? And so if you go to the bottom left of the screen, you'll see that it wants us to specify a thickness for the strip, okay? Because what it's modeled as right now is kind of like a 2D surface. And so ANSYS wants to know how thick this thing is on that surface, okay? And so the only thing we have to add here is that we have to add something really, really small just to make sure that it doesn't actually contribute to the simulation at all, okay? At least in terms of its structure, okay? And so the thickness that I chose for this is just 1 e to the minus 3 inches, okay? And if you're not in inches, make sure that you're in inches. And so to go to home right here and change your units to inches if you're not, okay? Right, and so just change this to something really small. And so I would say at the most it should be is 1 e to the minus 3, okay? I think a few people yesterday did 1 e minus 4 and that seemed to work out just fine too, right? But you just want this to be basically non-existent on this surface, okay? And one of the appendix notes that I talked about, I think a week ago, actually shows you it gives a little tutorial on how to do something like this, because this is actually really useful to be able to create a surface to apply boundary conditions on. Because what's common a lot, and actually a lot of people do this for their final projects, is they want to do some kind of simulation on a wheeled vehicle, so something like a skateboard or something like a car or something like that, right? And so in those situations, you would have like your wheels contacting the ground below your vehicle, right? And so in order to apply a boundary condition on just the parts where it contacts the ground, you need to create an extra surface like this in order to make that boundary condition, okay? And so there's a tutorial for that on Canvas. And so if you need to use that for either the midterm project or your final project, that's how you do it. It's not that hard. It's just kind of a little bit too much to go over in just one activity. And so for this one, it's already made for you, and so we don't have to do much for it. Okay. Yeah.
Since we're only applying the load to that phantom surface, would that affect I guess the stress analysis because it's not on the entire edge of the post?
Yeah, no, it would. Yeah, it would. It would change, of course, if you made this wider, if you applied it on the entire edge of the post. But the way that we're modeling here is that it's just going to apply a force on that strip. But yeah, whenever you change the geometry of where you're applying the boundary conditions, it's definitely going to affect the results. Yeah. Mm-hmm. All right. Any other questions on this phantom surface? Okay. Oh, one thing I almost forgot. And so the sign here is going to be made of aluminum. And so let's make sure that we do that. And so with the sign highlighted here, let's go ahead and change the material assignment from structural steel to aluminum. Okay. Yeah, and then everything else can be made of structural steel, and it's fine. Even the phantom surface, you'll see that the phantom surface is made of structural steel, and that's actually okay because it has such a small thickness that it's not going to contribute at all to the simulation. Okay. Okay. All right. And so this is one of the nice things about working with assemblies, because when you have an assembly of parts like this, you can apply different material properties to the different parts of your cap, right? And so in this case, where we have a sign that's made of aluminum, we can have that and have the other parts of the geometry made of steel. Yeah. Yeah. Yes. Mm-hmm. Okay. And so that's the geometry. And so now let's go over context, right? And so another aspect of working with assemblies is that you have to define how the different parts of the assembly are going to interact with each other, okay? And so here we have 3 different parts, okay? And so we have 3 different contact regions here, right? And so in order to get the contacts, you're going to go to the project outline, and you're going to click on this plus arrow next to connections, and you're going to click on the plus arrow next to contacts, right? And then what you can do here is you can click on each of the individual contact regions, and you can see, which two surfaces that they're that we're defining the interactions for. Okay. Let me go to an easier one just to see first. Okay. And so for me, this is contact region 2, but I think ANSYS kind of does this semi-randomly, and so yours might be a different one. But you can see from this, from the figures here, okay, right? And so when you click on a contact, you'll see that there's kind of three windows that show up, right? And so we have our normal 3D view, and then we have kind of almost like a picture-in-picture thing, okay? And these basically show which parts are being connected here, right? And so contact region 2 is the contact between the sign, which is the giant rectangular part, and the post, right? And the place where it actually contacts is just this little circle right here, right? And so you can manipulate the view inside this inside these little picture-in-pictures to kind of see those surfaces. Yeah.
Are you able to change contacts at a specific location? Or are they always predefined?
Yeah, so that's a good question. So whenever you have an assembly and ANSYS detects that certain parts are really close to each other, it'll automatically create a contact region for you. But you can delete it and you can modify it as much as you want, depending on depending on the nature of your simulation. Yeah. You can also define how those parts interact. And so when you go to this part of the details menu, right, you'll see that this contact here is defined as a bonded type of connection. Okay. And so what that means is that these two parts are basically going to act together as one, right? And so the way that you can think of bonded is that you can think of these parts as basically welded. They're basically welded together. Okay. Yeah. And so in the bonded case, ANSYS is going to treat them as one part. But if you click on this, you can see some of the other options that you have available, right? And so you can define those two parts to be no separation. And so what that means is that the parts are just not going to separate from each other, okay? But they can slide, right? Another way you can do is you can do frictionless, and so there's going to be no friction in between those parts, or you can have a frictional support too, right? And so that basically states that between these two parts they can move past each other, but there's going to be some friction associated with that, okay? So a lot of these different contact types, that I would say they're mostly used more for dynamic simulation, where you actually have moving parts. But for most static simulations with assemblies, most of the time you're going to pick a bonded support. Okay, and that's actually what we're going to pick for all of the parts here in this simulation. Okay. Question. So question is, so contact is mating two components together for assemblies. Yeah. So it's essentially the same thing. And so this is basically how you're defining the mating between those two surfaces. Yeah. Because once the simulation begins, then we're going to apply forces and loads and pressures and things like that. And so the whole model is going to deform. And so what this basically tells you is, what this tells ANSYS is how these two parts will interact with each other. In terms of once the simulation begins. And so by selecting bonded, you're saying that these two parts they're going to act as one. Okay. All right. And so if you go to the other contact regions, you can see that they define connections between other parts of the model. Okay. And so the first contact region is the contact between our strip and the side of the sign. Okay. And the third contact region is the contact between the strip and the post. Okay. All right. Any questions on contact regions? Okay. All right. So one small thing that you can do, and this is not required, but for more complicated situations, this is really helpful, is that you can rename your contacts, right? And so you can go to a contact region, you can right click, and you can rename it. Okay. And it's a lot of times it's useful to rename your contacts based on the parts that it's contacting, right? And so for this case, we have a contact between the phantom surface, if I can spell it right, phantom, and the sign. Okay. So a lot of times I'll just give it a simple name where I just name the two parts that they're in contact. This is the contact between the sign and post. Okay. And this third contact region here is the contact between the phantom surface and post. Okay. And so again, you don't have to do this. And for something as simple as this might seem kind of trivial because there's only 3. But you can imagine if you're working with an assembly with dozens of parts and hundreds of connections, it can be really easy to lose track of a certain one. And so if you're hunting down a specific connection, in those cases, it can really help to rename it. So you can kind of look at the list and read it really easily. Okay. Okay. All right. And so so the next part of the activity is the meshing. But there's really nothing new with the meshing here. And so I'm going to let you guys do that yourself, after I explain the boundary conditions. Okay. The only thing I require is that I want you to have 2 method objects and 2 sizing objects. Okay. Because what I want you guys to do is I want you to apply different meshing settings for the sign and different meshing settings for the post. Okay. And so for the sign, you're going to select a certain element shape and element order. Okay. And an element size, and then you're going to do the same thing for the post. Okay. When you're selecting your meshing size and methods, try to think about which parts of this geometry here are going to sustain the most stresses, or which ones are going to be sustaining the most loads. Okay. And so for that part, you should apply a much smaller mesh because that's where your stress is going to be concentrated, right? And so think about for a typical signpost or any kind of weight-bearing structure, right? And so where is most of the weight going to be, what part of this structure is going to be supporting most of that weight? And then you should apply most of your mesh density in that area. Okay. But I'll let you do that. I'll let you do that a bit later. Okay. Because one thing I do want to go over together with you guys is how to set the boundary conditions, because these are quite a few of these are quite new from what we've done before. Okay. All right. And so the first boundary condition that we're going to add here is we're going to add the weight of all the components. Okay. And so let's go ahead and right click on static structural A5. Okay. And the boundary condition that you want to add here is called standard earth gravity. Right. So standard earth gravity is it's kind of a special type of boundary condition. It's a boundary condition where you don't actually have to select a location, because what this is going to do is that it's going to compute the weight of all the objects in our assembly, and then apply kind of the gravitational force based on that, right? And so it's really convenient because it's you don't have to do anything. And so I'll show you. So after you go ahead and click this, okay, you can see that there's already a green check mark next to standard earth gravity, right? And so this basically says that we're going to be applying the weights for all the objects in this simulation. Okay. And then you can choose the direction for the gravity force, but here -z direction works just great. Okay. And so if you remember, from about 20 minutes ago, when we specified our aluminum material property, we gave the density for that material as well, right? And so the reason we gave the density was so that we can compute the weight using the standard earth gravity. Okay. Because if you don't input a density for that, then the standard earth gravity won't be able to compute a weight. And so it'll basically assume that it's weightless. And so, if you want this standard earth gravity to work with all your materials, you need to make sure you specify a density. Okay. Yeah.
Does it account for both FZ1 and WZ1?
Yes.
Both of them are included in this.
Yes. Yes. Yeah. Yeah. So if you look back at the project specs, you can see that I actually have separate forces there that have the weights, but this is going to take care of both. Yeah. Mm-hmm. All right. So the question is, for the default steel, do we need to add the density? So no. So steel is fully specified, and so it has its density. It has its Young's modulus and Poisson's ratio. It actually has a bunch of other stuff too, but it definitely has density. Yeah. Mm-hmm. All right. And so, I think a question that arises a lot is, what are some situations where you want to apply this standard earth gravity? Because, we didn't do it for the last 2 activities, right? And so the reason we're doing it here is because we have a relatively massive structure compared to what we've done before, right? And so for our first activity, we had a plate with a hole, which was kind of like a, kind of like a baby's first ANSYS thing. And so, that plate doesn't act, it's hard to imagine that plate actually existing in real life. And then for activity 2, we did kind of a dinky little bike crank. And so, the weights of those 2 objects were not really that significant. And so we could just ignore those. But for a very large structure like this, like you're talking something that's 28 feet tall, then the weight is going to be pretty significant in this case. And so that's why we're including it here, whereas before we didn't. Okay. And so that's the weight. Okay. Next thing we want to add is a point force. Okay. And so we're going to right click on static structural A5. We're going to go to insert and we're going to go to force. Okay. And then we're going to insert this force at a point. Okay. And so we've never done this before. And so let me just show you how to do it. Okay. And so if you look at the project specifications, you'll see that there's a wind force called FY1. Okay. And this is an 8,000 pound force that we're going to apply at the midpoint of this sign. Okay. And I know, we just got done talking about boundary conditions, and I know I told you not to do this. I told you not to apply forces at a point. And so typically you're not supposed to do this, but this is just for educational purposes, just to show you that it can be done. Okay. And so with the force selected here, we want to make sure that we change our selection mode to vertex, right? And so you're going to go to the middle of the screen here because these are all the different selection modes that we have. Okay. So go ahead and click vertex, and then you're going to kind of mouse over the middle of the sign right here. And then at a certain point, you'll see like a little dot that kind of gets highlighted when you mouse over it, right? It's a little bit hard to see with my mouse here, but you can kind of see that as I mouse over this point, this little point, starts to show up. Okay? And so we're going to go ahead and select that point. Okay. And so by selecting that point, it turned green. Okay. We're going to hit apply. Right? And then that's going to be the location where we're going to apply this force. Okay. This little point right here was very similar to the strip. So this was just a point that was sketched in Design Modeler and just projected onto this sign. And so if you ever wanted to apply a force or some kind of boundary condition at a specific point, that's normally hard to click in your model, then you can do that in Design Modeler too. Okay. And then the magnitude of this force is going to be 8,000 pounds in the y direction. Any questions on any of this so far?
Yeah, so I guess more realistically, you would apply the land to the whole surface.
Right. Yeah. Yeah. Especially for a wind force. So the wind is going to be acting on this entire surface, and so it makes a lot more sense to apply the force throughout this entire surface instead of at a point. But this is just to kind of show you that you can do this. In this particular problem. This point was selected very intelligently as right in the middle of this, big sign right here. And so it doesn't actually cause really any issues. Where you start to have issues is if you try to apply a force at this corner right here. Right? And so those can be pretty bad. But if you apply a point kind of in the middle of a large surface, then most of the time it's okay. But generally you want to apply it across the whole surface. Okay.
Is the reason because it would like cause a moment and maybe cause a failure?
So the reason it's bad, it's hard to explain it without getting into the numerics, but basically, remember we talked about finite elements, you're basically forming a matrix set of equations from all of these. And so if you apply the force at a single point, then all of that force is going to be concentrated on a single node. And so numerically what's happening is you're going to have a really, really large number in your matrix, and then everything else is going to be really, really small. And so it creates a lot of difficulties because those kinds of systems are called stiff. And so it's called a stiff linear system, and those are normally really hard. And so if you distribute the force over a whole surface, then that force gets balanced out between a lot of different nodes, and it kind of makes the linear system a lot more balanced. All right. And so there's one more force that we have to apply here, and that's the spatially varying wind force. Okay. And so let's go ahead and add well, actually, I believe it's a pressure. Okay. So let's go ahead and right click on static structural, and we're going to insert a pressure. Okay. And then we're going to apply this pressure on our phantom surface. Right? And so let's go ahead and click. You might have to go down here to do it. Okay. And so make sure you click the phantom surface just like that. So make sure that's highlighted green. And then we're going to click OK, hit apply. Yep, question.
Is pressure like a distributed load?
Yes, pressure is exactly distributed load. Yeah. Mhm. All right. Okay. And so now we're specifying a pressure on the strip. Okay. But we're not going to specify a value because normally when we specify a pressure, we just put a single value here. So normally say we say 5,000. And what that's going to do is that it's going to specify a pressure of 5,000. That's the same across all of this strip, right? But we don't want that in this case. And so what we want in this case is a force that varies with space, right? And so you can see here we have this kind of triangle distributed force where we have basically zero force at the base and then maximum force at the top, okay? And so what we're going to do is instead of putting a single value, we're going to put a function in there, okay? And that function, you can see right here, is just going to be 0.1 multiplied by z, okay? All right, so let's come back to mechanical, okay? And this part, and so before we input the function, this part's really important. So make sure that you're in inches units here, okay? Because then the pressure that you're going to be supplying is in PSI, right? And so make sure that you're in here. Otherwise, you're going to get some strange results. All right, and so to insert a function here, we're basically going to do, if you've ever input a function in like Google Sheets or Microsoft Excel, it's the same thing. And so we're going to hit equals. Okay. And so the equal sign tells ANSYS that we're inputting a function and not a value. Okay. And then we're just going to input the function itself. And so we're going to do 0.1 multiplied by z. Okay. And so if you do that, then your load will be specified here. Okay. All right. And so it was doing this yesterday, but normally when you apply this pressure, it should tell you, it should kind of give a reading here for what the pressure values are. Okay. And so you should actually see something like this. And so it should tell you basically the magnitudes of the pressures that you're supplying after you put the value in. But for some reason, this computer wasn't doing this yesterday as well. And so hopefully you guys can see that. Okay. And so if you want to check your results to make sure that your pressure force is all right, you should see a maximum pressure force of about 43.1994 psi, okay, or about 43.2. Right.
Yeah.
Any questions on this? Oh, question?
Yeah, over in Zoom. Yeah, I'm not getting that either. Should I apply solve in order to get it?
So later on, so when I did this, I clicked solve, it fixed it. But if it's not showing it right now, then don't worry about it. Yeah. Yeah. So if it just says variable load pressure, that's fine. So that's what it says for mine too. So yeah, if it's not showing up anything, yeah, don't worry about it for now, because I did this activity, front to back yesterday, and it ended up okay. Actually, there is one more thing I want you guys to specify, and that's a fixed support. Okay, and so we need to make sure we fix our structure. Okay, and it's just going to be fixed at the ground. Okay. Remember, when we talk about boundary conditions, you can't have a simulation without a fixed support. Okay. All right. Any questions on anything we've done so far? Okay. All right, so it's 6:10. That's everything I wanted to walk through with you guys, because that's all the new features. And so a lot of everything else is stuff that you've done before on previous ANSYS activities, right? And so you've done meshing, you've looked at results and everything, right? And so I'll give you guys about 20 minutes to work on this activity. Go ahead and apply your meshing settings, try to solve, and then take a look at your results, okay? And so if you have any questions about anything, just go ahead and raise your hand if you're in the class. But if you're on Zoom, just put something in the chat, or you can shout, and then I'll come back to the computer. Yeah. All right. Yeah. So if you're having issues finding the vertex on the middle of the sign, make sure you're in vertex selection mode right here. Yeah, or you can do Control P. That works too. Oh, did you mesh it? Isaac, maybe try looking on the other side of the signpost. It might be on the other side. Yeah. Jesus, did you create your mesh? Or are these all, do you see a green check mark here next to mesh? Let me go ahead.
I don't see a mesh showing up at all.
At all? So there's no mesh here on the side at all.
Right.
Oh. So do you have all the other stuff, but except for
Yeah,
mesh?
but not the mesh. That was kind of weird.
Huh, that's really weird. I've never seen that before. Do you see mesh up here on the top of the screen?
I don't. No.
Oh, that's weird. But you see the signpost geometry and everything?
Yeah. For some reason, the post itself isn't coming up unless I hover it with the mouse. Then I can highlight it, but it's kind of just shows up as clear.
Huh. Oh, that's very strange. Let's try resetting the workspace. And so go to home and then go to manage right here. And then go to, where is it? Go to reset and layout right here. And then see if that helps bring up the meshing.
Can you repeat that one more time, please?
Yeah, so you want to go to home.
Uh-huh.
And then you're going to go click this button right here called reset and layout. And let's see if that helps. Carrie, yes. So I want you to they don't have to be different, but I want you to apply settings for both the sign and the post. Yeah, but you can. But if you think it's appropriate to use the same settings for both, then you can do that. Yeah. But remember, you want to concentrate the mesh density and have your small elements where you think the maximum stresses are going to be. Jesus, did that help you get the meshing stuff back?
No, it wasn't showing up from the very beginning.
Okay. Oh, that's so strange.
Yeah, I might just try to redo it again from scratch after class.
Yeah. Try resetting the program and see if that helps. Yeah, sorry about that. I'm not sure. I've never seen that issue before.
Yeah, it's new for me. But thank you. I'll try it again. I'll try to catch you during office hours.
Okay. Yeah, go ahead and reset it right now, and then yeah, if it's still giving you issues, just send me an email afterwards, and then we can troubleshoot it then. Yeah.
Thank you.
Yeah. Yeah. Go ahead, Isaac. Let me stop sharing here. Okay, so go ahead and share your screen, and then we can take a look.
All right. Can you see my screen?
Yes.
Okay. So I have the vertex command on the top selected, and then I have a force on my tree over here.
Yep.
Now, when I hover towards the center of the pulse sign, I don't see.
Oh, I saw it. I saw it for a second.
Dot.
Wait, hover your mouse over the center again. It's right there.
That. Oh, okay. I thought it was like because I was doing this.
Oh, yeah. You have to
I was
do
rotating
regular.
the sign.
Yeah, regular
Okay,
mouse.
so just hover it. Okay,
there
okay.
It is.
Got it.
Yep.
All right, thank you.
Yep.
How do I stop sharing the screen?
There should be a toolbar near the top, and there's a red button called Stop Share. But I can force it to.
Oh, okay, I see it.
Yeah.
All right, thank you.
Yep. How's everyone in the class doing? Everyone doing okay? Sure. Yeah, that's another. But also, what I've seen that the values are really match up. And so I wouldn't worry about it. So if it's not showing up, just do the mesh, and then for me, it showed up after I did the simulation. So yeah, just keep going, and then hopefully it'll show up.
Probably like 3.9.
Yeah, I see that on mine too. I saw that yesterday and I was a little bit concerned when I ran the simulation. And it was actually
Okay, thank you.
So we have to,
Yep.
so.
Yep. Yep. So for the pose, you can actually use hexes for that too. So generally, if you can use hexagons, you should go for it because those ones perform better than text usually. Just the only thing is that sometimes, because the reason it's called text dominant is that sometimes it just doesn't work for certain geometry. And so for this one, you might struggle a little bit because it's curved. And so actually, I think about like maybe 4 or 5 people yesterday. And it depends, unfortunately, it depends on the computer. Some computers just refuse to do this on certain things. But usually, if you pick a small enough size, then you can put hexes on this. And so for this one, I would recommend try to do hexes on it and like make it small enough.
Okay. And
Yes. It's hard because it's supposed to just one whole block, and so you have to do kind of the same thing as a and so you have to go into the CAD and create something. But actually, what I would recommend, I would run the simulation. Because the simulation. And then from there, you can have to find.
I just did, he said, something like pixel.
Yeah.
Exactly.
So it's more like. Estimate it and check it. Right? So it's not like always the first shot. You can check on two or and it's not feed.
Yes. Yeah. So the sizing is the same. So you're gonna make one sizing for the sign and other sizing.
Should I start with like the default and then go down?
Yes. So actually, that's not a bad plan. So for
If it's like
exactly. Yeah. So the nice thing about this is that you
Oh, I
can
put
always
point
know
two
it's
last
the
time.
It's not. It's
On my.
no. Yeah.
Change your units.
So it's never a bad idea to actually,
Change
work
your
with
units,
the
you
default
keep it in
version
inches.
to as simple
I
as
think
you
that
can.
it was just.
And then kind of you can see the simulation and then adjust it.
Yeah, that stops it.
So I just picked like this.
Mhm.
And then I just, for this one, I just randomly picked 3 and the other one 2.
Okay.
Sizes.
Okay.
But I don't understand this one over here. Did you choose the same only sizes for the same? So I know it, but you said describe a situation where you just get 2 sizes for the meshes and the sides.
Mhm.
So
Right.
I did, but I don't know. I mean, just I randomly did it. I didn't do the.
So I would suggest you run the simulations first. So typically you would want a finer mesh or smaller element size where you see higher stresses. And so wherever your high stresses are, that's where you want to have bigger or smaller elements. And so I would say run.
This over here,
Mhm.
this area, like the circle one,
Mhm.
it will probably fail because that's what I think.
Okay.
Because of the wind over here and the weight.
Mhm.
So this would be like our issue, maybe the point of failure.
Run the simulation first, and then you can see.
So I have to add like solution.
Yeah. I see a question on Zoom. Yeah, if you accidentally close the details menu, you can go to reset layout, and then that's going to bring it back. And so make sure you're under home. Right. Okay. And then after you click home, there should be a button on the right here called reset layout. And so by clicking that, that's going to bring all your menus back. Yeah. Yep. finish this up. If it's taking more than, I would say, 10 minutes to make your mesh, I would be a little bit concerned. And so, yeah. Yeah, the mesh shouldn't take that long. And so if you want to see some references for what I picked, you should pick something that's in the inches that's greater than 2 and less than 10. Yeah. So sometimes, yeah, it's a good point. So sometimes you guys might get a warning, and actually I got it too, that if you picked an element size that's bigger than the global, all that means that one of your body sizings here is bigger than the default size here that's under mesh, right? And so if you go to mesh, this thing is so annoying. If you go to mesh right here, okay, then here you have a global max size right here, right? And so if you have an element size that's bigger than this, it'll give you a warning, but most of the time it's okay. So you can just ignore the warning. Okay. For most softwares, I would say if it gives you a warning, I would say most of the time you can ignore it because it's not going to stop you. At least that's the attitude that I take. But you know, sometimes it's worth listening to, but a lot of times I just ignore it, honestly.
What's the first part between those traces for this one?
Yes.
And 3 of this, right?
Yeah.
I think it's the orientation.
Yes. Yeah. If you guys accidentally picked a size too small for the mesh and it's still meshing, what you can do is you can go to the bottom right here, and then there should be like a little stop button. So you can click that to stop any operation that ANSYS is doing. Yeah. And so if it's taking more than, I would say, like 2 minutes to generate your mesh, I would stop it. You know, at least for this one, because it shouldn't be this mesh shouldn't take that long, yeah, unless you picked a really small size. All right, in about 5 minutes, I'm going to bring kind of everyone back, and then I want to talk about the rest of the activity, because the rest of the activity, I want to make sure that everyone kind of knows, well, what I want you guys to do for the rest of it. So, you know, keep working on it for the next 5 minutes. You know, if you can get the simulation results, that's great. But if not, you know, don't worry about it. You can finish it up later. But I do want to discuss the rest of the activity just so you know what to do.
Oh, it's just a general.
Okay.
So did you make the element sizes on the post smaller because you knew that there'd be more stress there anyways and you wanted it to be?
Exactly. Yeah. Yeah. Because I knew the post here was going to be supporting all the weight. And in fact, because we have this kind of lopsided geometry right here, then we almost have like, if you turn it sideways like this, then it looks like we have like a cantilever beat, right? And so a lot of the stress and most of the bending is going to be right here. And so that's why I chose a small size for the post.
Thank you.
I just add all the solutions on these
Yeah.
and run the simulation. It gives me this, and I'm really doing the solution to solve the article. The solution information. And this one's getting rid of it.
I would start with just the total deformation equivalent stress. So you can just right click all of these ones. So down here and then just suppress it. Yeah, so just suppress it because you've already set the settings. And so just suppress it and run it. And see if it's like-
So I just have a question. You said we
And then we
take
just
gravity.
Yeah.
How large would it have to be? Or does it have to take into account gravity?
Yeah, no, it's a good question. And so usually if the weight of the object is, I would say on the same order of magnitude as the other loads. And so if you're talking like let's take the bike. And so the main load that we put on there was 100 pounds. And so if that bike crank weighed like kind of something close to that, maybe like 50, 60, 70 pounds. Okay, I would say that's significant.
So like, if I were to do an analysis on like, let's say, chassis formula, would I take into account the weight of that?
Yeah, I would think so.
Okay,
And you can always turn it off. So you can always do a test with it on and then without it. And so you just
I couldn't put it.
and you can say that it's needed, but it's not.
Did you just leave? Yeah.
No, I told the, we'll just do the links. She said it was like a wheelchair.
Oh.
So you can add by holding control and then
Was your element substitution?
and then click on the
So we don't touch them.
and hold control.
This is last 2 weeks ago. We don't touch it this season.
It's a little bit annoying. So panning is just something that you.
I think he said just the falls a guy.
Your
Your object.
It took me a while.
Global one, he says that they need the.
But he said the.
Your individual sizing ones.
You have to-
less than the global one.
Last year, you said, you always have to fix.
Yeah, so go to result. I still have that one as well. Right next to pause. And then you can go to. Yeah.
So here it says. Change the sign of such multiple constraints. You put this here.
Yes. Oh, no, you're just gonna read the maximum stress and see if it exceeds this amount. So just like a 50.
So you have to adjust until it reaches like 5,000.
So this is normal stress and the stress. So check the normal stress and the Z.
Oh, it's 30.
Okay. So this is where most of it's gonna be. So that's.
So you have to adjust based on, and then you have to try to get into the next part.
Exactly. Well, for this one, I'm not gonna have to change the loads. And so the loads here are gonna be the same. But we'll talk about it in a minute. So what I'm gonna have you do instead, because this is more for most cases.
Honestly, I actually didn't want
And we're gonna move on. So we're gonna change. So we're gonna do like kind of the opposite of what we did.
Yeah, so based on the mesh for like if I want to get this this value, I would have to change the mesh and make it smaller size.
It'll affect it a little bit, but this is already pretty accurate, so that's kind of close to what I have. And so the mesh is only gonna cut down, but the loads are all gonna be, so that's all we're gonna do. So we need to actually change the geometry or changing the material of the sign. So I think we all know our parts are in it.
Okay, so, but I like for now, I do the.
Yeah, you're good for now. Just chill and stuff.
With my legs.
Yeah. So I heard for some people, for some computers, I don't know what it is, but like it really struggles with X meshes on certain ones. And it could, it's honestly, it's probably just like activates today. You do it tomorrow, it's gonna be fine. So for the post, I would change it to tetra. Can you have a question?
No, it was just the fixing one.
Oh, okay.
I had
Thanks.
for the post that one. This one.
All right, hey Colin, yeah, sorry about that. Can we, I'll help you out after class, but let me just do 10 minutes just to let everyone know what the next steps of the activity is. Yeah, okay. And so let's bring it back just for 10 minutes, just so we can talk about how to do the rest of the activity. Okay. And so if you were able to finish the simulation, you should see. And so I didn't add all the results here, but the equivalent stress you should see is around 28,000, 29,000, depending on your mesh. Okay. But the upside to this is that if you assume that the post has a yield strength about 25,000 psi, then this post is going to fail, right? And so in problem 5, what I want you to do is I want you to improve the design of the signpost such that it's not going to fail, right? And so you can do this in a few different ways. And so I'm not going to tell you to do one way or the other, right? And so one way that you can do it is you can change the material of the post, right? And so if you want to use a material that's stronger than steel, then you can feel free to do that. The only thing I would say is that if you're going to change the material, make sure it's a real one. So don't use like vibranium or something like that with like, and say it has like infinite Young's modulus, right? And so make sure it's a material that actually exists on Earth and not in movies, okay? Right? And so that's one way you can do it. And I want you to do some research on that just to make sure that that material exists and is feasible, okay? The other thing you can do is you can change the geometry. And so let me run through that really quick just to show you what you can do. Okay. So I'm going to close mechanical for a second, and then I'm going to edit the geometry here in design model. Okay. Because whenever you have kind of a post like this or some kind of weight supporting object, it becomes a lot more stable whenever you increase the diameter of that post. Okay. Or whatever the column that it's that's supporting it, right? All right, and so it's kind of a mess here because I was kind of messing with this geometry a little bit, but if you go to sketch 1 here, okay, and so sketch 1 is under XY plane, what you'll see in the bottom here is the diameter of the post, right? And so actually, if you zoom in to this part of the post down here, you can see that the circle that we're modifying is here, right? And so what I'm going to do is I'm going to increase the diameter of this post. And so instead of 1.12, I'm going to change it to say like 1.3. Okay. Don't make it too big, otherwise it's not going to fit into the slot. And so don't make it like 2. I already tried that and it didn't work. And so only make it a modest increase. Okay. And so I'm going to go ahead and hit generate. Okay. And so that's going to increase the diameter of the post. So let me go ahead and close this. Yeah. Mm-hmm.
Is there a tool to measure that the bottom of that post?
There is in Design Modeler, but in ANSYS Mechanical, I haven't found a good measuring tool for that yet. Yeah, there is a ruler here, and so you can do kind of like an approximate measurement, and I'll show you in a bit. And so you can use this ruler down here at the bottom of the screen, and you can do kind of like approximate measurements like this, but exact like caliper tools, those are usually best done in the CAD software. All right, and so you can see here my post is a little bit thicker now, right? And so the nice thing about this is that it saved all my meshing settings and boundary conditions. And so I'm just going to hit, actually, just so we're not meshing for days, let me change this up to 3. Okay. I hit solve. And so remember, before I was getting an equivalent stress of about 28 1,500. Okay. You'll get this warning. That's okay. Right, and so you can see just by making the post a little bit bigger, a little bit thicker, you can see I've decreased my maximum stress down by about 10,000. Right, so that's pretty significant with it. Okay, and so that's one way you can change the geometry of this signpost in order to make sure it doesn't fail. Okay, another creative way that you can do it is you can reduce the weight. And so one way you can reduce the weight is you can reduce the thickness of this sign. Right, so you can just make it simply thinner. Right. And if you make it thin enough, that's going to reduce the weight such that it's not going to place as much force here. Okay. All right. So be creative. And so you can do, any one of those things to design the post. Right. Okay. And so that's problem 5.
Can we also decrease the length of the post?
You cannot. And so the one thing is it has to maintain the same height. Yeah. Mm-hmm. Yeah, because if you do that, then trucks are going to hit it when it drives past it.
Oh, that makes sense.
Yeah. Mhm. Yeah.
Can you orient the post in a different way?
You could. Yeah. If you want to do that, you can do that as well. Yeah, as long as you maintain the same overall height, overall dimensions for the signpost, you can do anything you want for the design. Yeah.
You can still do that in a design model.
Yeah. So it'll be a little bit hard, and so I would say that's probably not going to be the most convenient way. But if you wanted to do it, then by all means, then you can do it. Okay, and so that's problem 5. Problem 6, I want you to come up with different loading scenarios. Okay, and so what we have here is just one way to load this this signpost, right? And so we have the weight of all the objects. We have a wind force that hits the middle of the sign, and we have a pressure force on the outside. Okay. But there's lots of different ways that this sign can be loaded, right? And so the wind could be coming from a different direction. It could have a different magnitude, right? And so you can mess with the directions and magnitudes of these forces. Okay. You can also model things like maybe there's a bunch of really fat seagulls that sit on top of the sign, right? And so you can add an additional force on top of the sign for that. Okay? Or maybe some prankster, tied his washing machine to the end of the signpost right here, and it's hanging from there. Right, and so that's another force that you can add, right? And so be creative, and so modify the loadings for this signpost into 2 different configurations, and then run the simulations for those. Okay, and then I want you to show the following results for that. Okay. All right, and then problem 7 is just just like the last activity. I want you to summarize your findings. Okay, and so just to do a one page summary. Okay? Make sure that you have at least one figure in here, okay? And so, pay attention to this one. And so I was a little bit lax with this on the last activity, but, whenever you're showing your finite element results, say you're doing it in an email or a quick report to your manager, they're going to want to see at least one screenshot of your finite element results. So make sure that you include that, okay? And then problem 8. And so problem 8 is a finite element analysis of a chair. And so for you guys, this one will be optional, but if you do it, then it'll be just like the last one. It'll be another 10 points extra credit on the assignment. Okay. But if you want to do the finite element analysis on this chair, then the CAD file for that is here. Okay. And so it's called assembly.step. Okay. All right. So are there any questions on the rest of the activity?
Question from Zoom.
Okay. Oh, question?
Yeah, for the activity, for the page summary, is there such thing as overkill with applying too many figures onto the report?
There is, and so you want to make sure it's concise. And so if you add too many figures, then it becomes a little bit too much to read. And so think of it as like, your manager only has like maybe 5-10 minutes just to see what you're doing with this analysis, and you want to make sure that they can read and understand everything in that 5-10 minutes.
Okay.
Yeah.
If we change the material in the post design in number problem 5.
You can do that.
But is the yield strength changing? I mean,
oh yes. You can assume that the yield strength stays the same, but it's just the Young's modulus would change. Yeah. Mm-hmm. Yeah. Good question. All right. Any final questions before I let you guys go? Okay. All right. So I'll stick around for the next probably 20 minutes because I know some people were still having some issues, but that's the end of the activity, and so I won't hold you guys anymore. So Thank you guys for coming to the activity. Hope you guys enjoyed it. Have a great weekend, and I'll see you guys on Tuesday. All right, Colin, do you want to share your screen so I can help you out?
Yeah.
Did you close it? Oh, you know why? Oh, okay.
All right, so getting red arrows. Okay. Okay. Can you click on the bottom of the screen? So do you see where it says one message? Let me see what that message says. Ah, okay. Yeah, so your mesh is too fine. And so do you see, so the error is that you have too many elements in your mesh. And so if you click on mesh right above body sizing, let me see how many elements that you have. Right above that. Yeah, so go down and click statistics in the bottom left. Okay. Oh, you're just barely over it. So you need to for the student version, I think you need to be under 32,000 elements. And so I would recommend making the element size in the sign a little bit bigger, just so that there's less elements. Yeah.
I think that's why I had it before, and I was getting more errors then.
Okay, let me take a look and see.
I should have 4, not 3.
Good one. Huh. Where's your fixed support? Let me see that.
Very bottom.
And so it's applied at that totally bottom surface, right? Okay.
Yeah.
Okay. Huh. That's really strange. Can I see the magnitudes of your forces and your pressures? Okay, pressures. Let me see.
Oh, I might have not done anything for pressure.
Okay, can you switch to workbench? I want to check the material properties for the. So click on engineering data. Let me see your aluminum. Okay. Okay, yeah, these look fine. I go back to mechanical. Let's see. Can I see the body sizing for the post? For the cylindrical post. Okay. Let's increase these quite a bit actually. So let's go to body sizing 2. Let's go to body sizing 2. So I want to change the size of the ones for the sign. Yeah, so let's go ahead and change this to change it to 7.
All right.
All right. Let's try running this and let's see. That's fine. Yeah, don't you that warning is fine. Can I see the WX2 application surface? Let me see sign solid body. I see post solid body. Yeah. Can I see all the contact regions? Number 2. Number 3. Huh. All right, can I see your hex dominant methods 1 and 2? Can you choose a quadratic element order for the instead of using the global setting? Yeah, do quadratic and do that for the other one too. All right, let's give it a try.
just want to leave my stuff and come back and write.
Still.
Alright, sorry. Okay, I'll be back then. Thanks.
Can you double click the error and let me see the that's so weird.
Should I just restart basically?
Let me see the standard Earth gravity. Let me check mine real quick. Yeah, Luke, I see your message, Luke, and so let me let me try to help Colin first, and then we'll see. Okay, yeah, that looks fine. Go to try going to analysis settings. Can you go down to solver type? It's a down a little bit, up a little bit. It's under solver settings, right there. Yeah, and try doing direct. Okay. Go ahead and then try solving it. Okay, try instead of direct, try doing the other one, iterative.